Okay, so we started, we finished at a question where we wanted to calculate exerted torque on a loop. And we said that after calculating the magnetic dipole moment, we found that, as you can see here, that the magnetic dipole moment, due to the current rotating clockwise, the magnetic dipole moment was pointing in the positive y direction, which is the same direction of the magnetic field, and that's why the torque exerted on that loop was 0. Okay, so today we will continue looking at the general case where basically the magnetic field is either non-uniform or the direction of the current is non-straight. And in this case, we have to use the general case, which is the integration. So as you can see here, the general case is the differential format for the magnetic force. dF vector equals to I dl vector cross B vector. In this case, as I said, either the magnetic field is non-uniform or the direction of the current is taking is not being straight, is changing. In this case, we will have to use the general case, which is the differential case. As you see here, in case the first case, I have current going in a straight line. However, the magnetic field is non-uniform. The magnitude is changing. Then you have to use the integration. Second case, the magnitude is constant. However, the direction for the magnetic field is changing. This is going to result in, that's a vector field, so it's going to result into different values of forces. That's why we need to take the integration. The third case, although we have the magnetic field as uniform, but the current is constant, for example, but however, the direction is changing. This way we have to take also the integration in those cases in general. Okay, so how do we calculate the magnetic force in case I have a variation? The force is non-uniform on that wire. In this case, as I said, I have to use the integration. So let's look at this example. In this example, we have a wire that has been aligned horizontally on the x-axis. The current is going in the positive direction, and the wire is at the starting point of the wire is at x equals to d, ending at x equals to d plus L. And we need to calculate the magnetic field, the magnetic force due to this non-uniform magnetic field that is given by C over X, aligning on the y-axis. So, as I said, we have the coordinates X, Y, and I have the wire from D to with the L. So this point will be D plus L. Okay. Now the magnetic field given by B equals to C over xj. This is going to look like multiplied by C. So in general, this is how the magnetic field is going to be aligning along the Y, as you can see, changing based on this equation. Okay, so the first thing we put the general equation, which is dF equals to I dl vector cross B vector. The most important thing that you should be aware of is how to represent that, because B equals to C over X, not U. C over X. Yes, this is the magnetic field. So the most important thing is how to define the differential element. My differential element here, let me use another color. This is my differential element. So this differential element is moving along the X axis, which means this differential element will have my variable to be as a dx. And since this one is a vector, then my direction of motion here, in this case, because it's a line along the x, will be I hat. So this is the most important parameter that you need to define it correctly. And then the rest is only the cross product of a magnetic field that the equation has been given to you. So if I am to put now things together, then my df will be I, and again I'm taking the direction of the coordinate as my positive direction, and I let my current decide on my actual direction. It is B. It is B, not dB. I have df, and then I have my differential element as dl. It is one variable here. It's a differential element. My magnetic field is defined by the equation that describes this magnetic field as a vector field. So I let the value of the current, decide on my sign, and I write my dl, my differential element, using the positive direction as the direction of the coordinates. So in this case, I have dl vector equals to dx along the I. So now I substitute dl with dx I. This is across b, which is c over x j. So this is my differential equation that I need now to integrate. F is within the limit of x, my variable, is going from d to d plus l So I have I dx I hat cross C over X J hat. So this gives F equals to, let the I go outside and the C go outside, and I cross J equals to K. So I have I, C, and then K hat, because we know that I cross J is going to give me K. As long as I go with the positive direction, I get a positive answer, which means I hat cross J hat is going to give me K hat. However, if I go J hat cross I hat, I'm going in the opposite direction, I will be getting minus K hat. But since I'm going I hat cross J hat, I will be getting K hat. So the cross product here between the I hat and J hat is K hat, and I'm only left here with X equals to D plus L of dx over X. And this is F equals to I C K hat for the natural logarithm of X for X equals to D plus L. And this gives F equals to I C. This is logarithm D plus L minus logarithm D for K hat, which means F equals to, the subtraction of two logarithms is indeed the logarithm first one divided by the second one. So I have I C logarithm D plus L over D in the direction of positive K. So this is the net magnetic force applied on that wire due to a non-uniform magnetic field along the x-axis. Along the y, the magnetic field is along the y-axis. However, it is non-uniform along the x-axis. Any question about how did we calculate the net force on that wire? C is a constant coming from the magnetic field. We said that the magnetic field is given as C over X. C is a constant. Any other questions before we move on? X is how is the current, or the direction of the direction of the current that is moving along. So if we go back to the figure here, you will see that the current is going in this direction, along the x direction, in the positive x direction. And you have the magnetic field is varying along this x, however, oriented along the y. So at every single point, you can see that the direction is y, however, the magnitude is changing based on this equation. No, it's not uniform. The word uniform means magnitude and directions are the same everywhere in the field. Okay, so let's move on. Now let's look at this question. In this question, we are asked to find the direction of the net force applied on this semicircular wire lies in the XY plane. And we should be able, by inspection, if we understand the equation of the magnetic force, to get an idea about what direction of the magnetic force should be applied on this semicircular shape. Let's see how does this work. So in this case, as you can see, we have a semicircular wire lies in a plane XY. The positive Z direction is out of the plane. So we have the Z out of the plane. The wire has a current I going counterclockwise in a uniform magnetic field. Notice that the magnetic field is uniform, has the same, it looks like it has the same magnitude and the same direction, directed along the y-axis as we see here. What is the direction of the net force acting on the wire? Okay, so if we look at this problem, we notice that I have a uniform magnetic field. However, the direction for the current is changing, taking a semicircular shape. So what does this mean? This means that for the first half of this wire, I have the direction going in a curvature shape all the way up to this point, which means that at any point, let's take that point, I have my direction being decomposed into a vertical one and a horizontal one. All the way, I start from here with a pure vertical right at this point, and then a second component will start to show up till I reach this point where I have a pure horizontal. So during this path, half of this semicircular shape, I have my direction going this way, which means at any point in between, I have a vertical and a horizontal. The vertical one is parallel to the magnetic field, is going to contribute to zero magnetic force. So the only force that is affecting my magnetic force is this horizontal that is pointing in this direction. Now, same thing happens to the second half, where basically when it rolls down, when it rolls off this way, the direction is like this, which means it can be decomposed into two components. One of them is vertical, anti-parallel with the B, and the second one is horizontal in the same direction. So the force that is affecting the direction that is affecting my magnetic force is always being horizontal going in this direction, which means if I am to unvarying, as you can see, from 0 all the way to maximum, going back to 0. So if I want to calculate the or know the direction of my magnetic force, it will be taking the cross product between this vector and my magnetic field. So this is the L, and my B is pointing up. In this case, I will be going in this direction. I will curl in the direction of the magnetic field. Then I have my force applied on the semicircular. All forces on that semicircular shape are pointing into the page. So the answer here would be D, and the negative minus C pointing into the screen. It's not they cancel out, Muhammad. The vertical component in the first half is pointing upward, which means it's parallel with the magnetic field, which means they will contribute to no force. Why? Because the cross product between them will be zero. The same thing for the second half of the semicircular shape. You have uh, the, the component vertical pointing downward is anti-parallel with the magnetic field, resulting into a cross product of zero as well. So the only component that is affecting is the horizontal component, and as you can see, those horizontal components, they all point in the same direction. And that's why the force that is effective or contributing to the net force on this semicircular shape is the vertical one, and that's the one that is causing the net force on this semicircular shape. And that force is pointing into the screen because the direction of the of the motion is this way. Up is the direction of the magnetic field. The direction of the magnetic force will be pointing into the page. And yes, the current is in the same direction here. That's why the current is the one that decides on the direction of the force. If the current is negative, if I is negative, this means the force would be out of the page. If the I is positive, this means the force would be into the page. We're going to come into the derivation or solving this problem analytically. I just wanted to explain to you uh, just by inspection. If you see this problem by inspection, you should be able to understand what is happening in terms of the reaction between the current that is taking the circular non-straight shape and the magnetic field that is uniform there. Now we're going to move to solving this problem. So we have here okay, so we have X, Y, and this semicircular shape, current I going in this direction, and then we have radius here, R, and we will take this part as my DL. And I will call this angle theta. So if I am now to put the equation for the magnetic force, it would be dF equals to I dl cross B. So what is dl here? dl is a differential length, and it's a vector in this case. So my dl here is moving along this arc, which equals to r d theta, and the motion is happening along this B is pointing uniform this way. The motion is happening along the theta hat. So where is that theta hat? Theta hat is perpendicular on the radius r. The motion is happening on that semicircular shape in the direction of theta hat. So this is my differential element. dl my magnetic field B is along the y, uniform along the y positive, in the direction of the positive y, which means it is the by, the y component, j hat. Now I can put everything together, where df equals to I r d theta hat cross by j hat. This is my differential representation of the magnetic force along this semicircular shape. Now I need to integrate. I will be integrating from theta from 0 to pi. So I have f, and I will take out all the constants. I have I constant, I have r as a constant, I have by as a constant, I have integration from 0 to pi for theta hat cross j hat d theta. Now, how can we calculate the theta hat across j hat? We've seen how we can do the cross product between the Cartesian unit vectors I, j, and k. But what about theta and j? Well, if we zoom in and focus only on those unit vectors, let me take the coordinate here, x, y, and take this one as my vector. Let me call this one as r. Then my x and y unit vectors would be at this point as I hat that is perpendicular on j hat. However, if I go to the polar coordinates, I can see that this vector, I have r hat along the vector r, and I also due to the circular motion here, theta, I will be having a vector that's called theta hat. Now, if I call the angle theta, if I represent the angle theta by a dot, and the angle pi over 2 minus theta as two dots, then this one would be a dot. This one will be two dots, the complement. This one will be a dot, right? And the angle between the j and theta would be theta. Now remember, when we take the cross product between any vectors, A cross B as A magnitude times B magnitude times sine theta in between. Now the direction for A and B will also follow the cross product If you recall, we said that for those three fingers, if I have this as A and I have this as B, then the thumb will be A cross B. Now this is if I have two vectors that I am taking the cross product with. Now assume if the angle is not 90 degrees, then I should not forget the sine theta. I can still apply the same concept where the cross product is also perpendicular on the plane that has the A and the B. This one is perpendicular, but the magnitude will be different. Why? Because the angle between A and B is not 90 degrees. So in this case, my theta cross J, because the angle is not 90 degrees, would equal to sine theta. And as you can see, if this is theta cross J, then put them this way, theta cross J, then the results will be going into the minus Z, which is minus K hat. So theta hat cross J hat equals to sine theta, because the angle is not 90 degrees and the direction is going into the minus K hat, because if you take the right hand also using the fingers, go from theta toward J, from theta, go toward J. So this is the theta curl toward J. It's going to give you the result of the cross product, which is in this case pointing in the negative direction of the Z, and that's why it is minus K hat. So now I have the force F as minus I R by integration for sine theta d theta, where theta goes from 0 to pi. F equals to minus IR by minus cosine theta, theta from 0 2 pi. Integration for the substituting f, take the minus outside. I have I r bw cosine pi minus cosine 0. This is going to give me minus 2, and then of course k hat, and then f equals to minus 2 I r b y k hat. Any question? We're talking, Emilio, we're talking about the cross product of, we're not talking about the I here. Here we are talking about the cross product between the theta hat and the j hat with an angle of theta in between. The cross product of theta hat and the j hat is going to give you minus k hat. Now, since the angle is theta is not 90 degrees, then it will be sine theta minus k hat. Let me see here. No, the minus came out to here. So this is IRBY, integration of theta plus j. The answer was sine theta minus k. So minus k, minus here, k hat here, sine theta here. And then when we integrated, the minus canceled, and then the answer for the substitution of pi and 0 was minus 2. Ended up with f equals to minus 2 IRBK. Yes, yes, I am posting the recorded lecture. Any other questions? We have a minus came from the integration, right? When we did the integration, we got a minus. This minus canceled with the minus that came from the minus k hat. Now, when we, after we substituted cosine pi minus 1, so f equals to I r b y minus 1 minus 1 k hat, and this gives f equals to minus 2 I r b y k hat. Okay. Any other questions? Okay, so let's move on. Now let's go to the recent slides that I uploaded. So in last lecture, we talked about the magnetic field generated from a constant current going. Yes, that's true. A constant current. We are going into a loop, and we saw that using the right hand by taking the direction of the current with the fingers, I managed to get the direction of the magnetic dipole moment, which is the same of the direction of the magnetic field within that loop as the direction of the thumb. Now, if I have a straight wire with the current going straight, this wire is also generating magnetic field. However, those magnetic fields will be circular and closed surrounding the wire. So if we look at this case where we don't have a current going into this wire, then you can see that those compasses are aligned within the magnetic field of the Earth, such that the magnetic dipole moment is aligning with the magnetic field of the Earth pointing to the north because there is no current. However, if I run a current going upward into that wire, then this wire is going to generate a magnetic field around it. Those magnetic fields are going to look circular in shape, so surrounding. So in this case, if I am to draw the magnetic field here, they will look like this. And since the current is moving up, take your thumb as the direction of the current, and this way your fingers will give you the direction of the magnetic field. And in this case, since the current is going up and following the right hand rule with the current pointing up, your thumb is pointing up, your fingers defines the direction of the generated magnetic field, which is in this case is counterclockwise. And as you can see, this will be the direction of the magnetic field. Okay, that's why in this case all the compasses will align now with this magnetic field, such that the magnetic dipole moments for those compasses are along the generated magnetic field surrounding this wire. Now, if I have the current going into the screen, then the magnetic field is going to be circulating around that wire such that it is clockwise, because now your thumb is pointing toward the current, and now your fingers are going to be rotating in the direction clockwise. Now, at any single point on those magnetic field lines, the magnetic field will be tangential and pointing in that direction. So if I want, for example, to calculate or to know the magnetic field at that point, then it will be tangential to this magnetic field line and pointing in this direction. If you take this one, again, tangential and pointing in this direction, this point, it will be tangential and pointing in the same direction. So this is how, exactly the same way we looked at the electric field. If you recall, they were tangential to their electric field lines. So by evaluating this magnetic field, and the experiments showed that the field lines here are the lines that defines the direction at every single point, right? Only a visual representation to how are the magnetic field pointing at any single point around this wire. Now, the experiment showed that this magnetic field is proportional to the current going into that wire and inverse proportional to the distance squared. So the greater the current, the higher the magnetic field, the further the evaluation point or the observation point from the wire, the smaller the magnetic field would be, such that it is inverse proportional to the distance squared. However, the direction here is different, and this is similar to what we have seen in the electric field before. However, the direction for the magnetic field is different. It is not along the line between the current and the point of interest. No, it is the cross product between the current direction and the point of observation, or the vector between the differential element and the point of observation. So we will see this shortly. Uh, the equation that represent this magnetic field is given as this is B equals to mu naught, where mu naught is the permeability of the free space, and integration for the differential element dl vector cross the unit vector of the displacement vector between the differential element and the point of interest divided by the distance squared. If I am to represent this equation with the differential representation format, it will be dB equals to mu naught I divided by 4 pi times dl cross r hat over r squared. So as you can see here, the direction for this field is not going to be along the displacement vector. It will be the result of the cross product between the differential element and the unit vector of the displacement vector. So we have seen R, we know R, we've dealt with R before in the electric field. It's the displacement vector, and the R hat is the unit vector of that displacement vector. The differential element dl is a bit different here because it is a vector, it's not a scalar. So we have to include the unit vector for this displacement, for this differential length. And mu naught is the permeability of the free space that is given as 4 pi 10 to the power minus 7 for the free space. So how do we derive the field representation or field equation for a line that has a current going through? This is called the Biot-Savart Law. This is the Biot-Savart Law that we have introduced, and now we will see how we can calculate the magnetic field for this line that has a current going through. We have a line and coordinates. If I have my coordinates as x and y, and my line is being laid on the y with a length of 2a, varying from minus a to a, and then my point of observation here is x. Then if I take a differential element being dl here, and this differential element is defining a vector r between this differential element and the point of observation. I need now to calculate the net magnetic field right at this point. So I will go now to the general equation, mu naught I divided by 4 pi times dl vector cross r hat over r squared. So the first thing I said is the differential element here, dl. We know that dl is moving along the y-axis, which means that the dl vector equals to dy. My variable is dy, and my unit vector is j hat. So this is my dl. I define my dl. R, again, we have seen how we can represent R here in case of an X and Y. I will be varying along the Y axis, so my variable is going to be dy. I want to make everything in terms of Y and X. So I have R here, R hat. Don't forget that this R hat equals to R vector divided by the R magnitude. We've seen that before in the electric field. So what is this R hat, R vector? This R vector, if I am to represent it, it will be decomposed into two vectors. The first vector is this one, and the second vector is this one. So what's this vector? This vector is y minus j, and this vector is xi. So r would be equal to xi minus yj. This is r. What is R magnitude? R magnitude is x squared plus y squared. Or I can say R as x squared plus y squared half. Same, no difference. So I now have R, I have R magnitude, I have the differential element. I need to substitute in my equation. So dV equals to mu naught I over 4 pi. No, let me leave the integration now for the time being and continue with the substitution times my dl is dy j cross my r is xi minus y j divided by, in this case, if I am to substitute r hat with r vector over r, then here becomes r cubed. Then this one becomes r cubed. So magnitude cubed, I have the magnitude as half, then this becomes x squared plus y squared 3 over 2. Okay. Now, if I am to look here at the cross product between j and j, the result would be 0. We all know that the cross product between a vector and itself is 0. So I will only have the result of the j hat cross I hat. And I know that the I to j to is k. So I have j cross I is minus k. So this is going to result into a useful product. However, this j is, with the cross of this j, is going to give me 0. And the answer to this would be, because of this one minus k, it will be minus dy k. So dB is mu naught I over 4 pi times minus dy k hat over x squared plus y squared 3 over 2, right? Now I can find the put the integration, b equals, let me take the mu naught I over 4 pi with the k outside. So I have minus mu naught I over 4 pi k hat outside. And I have now the integration from y equals to minus a to a for oh, yeah, we forgot we forgot where's the x here? It's x dy, x dy, right? The product of dyj cross xi is x dy minus k. So we have x dy minus k hat. So now the integration inside would be for x dy over x squared plus y squared over 3 over 2. Okay. Now this integration does exist in the table of integrations, exactly the same way we used it for the electric field. Then substituting this integration, it will give me b equals 2 minus mu naught I over 4 pi k hat. Now the integration here is going to be y over x squared plus y squared minus a to a. Now substituting minus mu naught I over 4 pi k is going to give me here y a over x squared plus a squared minus up there is going to give me minus a over x squared plus a squared, then b equals 2 minus mu naught I over 2 pi, take the x outside for a over x squared plus a squared k hat. And this is the magnetic field due to a finite wire. I am integrating from minus a to positive a, which is 2a. Okay, we're done with our lecture, and now I'll take your questions before we end the lecture. Do you have any question? It is a minus a becomes 2a. A minus a becomes 2a, and the 2 then will cancel with the 4 Yeah, the X went out. The X. Okay. Thank you. Thank you. Bye-bye. Thanks. We'll see you on Monday. Thank you. Thanks. You're welcome.